discussing electromagnetic theory, and today we're going to talk about the continuity equation. Also, we're going to derive Maxwell's first equation in differential form. Well, the continuity equation is a manifestation of the law of conservation of charge. The exact statement of that we're going to use to derive the continuity equation is basically a form of conservation of charge. So let's assume that we have this volume which is bounded by the surface S, and this volume has a certain charge density rho. The magnitude of the volume is V, capital V, and of course the area is the surface S. So if due to some reason there is a decrease in charge density within this volume, then that should be equal to the charge crossing the boundary surface per unit time across the surface that bounds this volume. In other words, the charge cannot be destroyed. So if there is a decrease in charge density, charge has to go somewhere. And in this case, there's nowhere else to go rather than cross the boundary surface and constitute this current I. So we're going to start with this statement and use some mathematical formulation to arrive at the continuity equation. So the total current flowing out of some volume must be equal to the time rate of decrease of charge within that volume. That's a statement we're going to try and analyze and use to find the continuity equation. So again, let rho be the volume charge density within the volume V, and if the charge is decreasing per unit time within the volume, that decrease of charge per unit time should be equal to the current, and which is given by equation 1, where current is the rate of flow of charge flowing out of the volume, dq upon dt, and that should be equal to the time derivative of volume, the charge within the volume, which is the volume charge density times the volume, the net volume. Now let's assume that the current density here is J. So we know that the current density is the current per unit area. So if you want to represent current by current density, then that should be the surface integral of J dot ds. And that gives us our equation 2. And plugging back this equation 2 into equation 1, we have this equation 3 where it says that on the left hand side we have J dot ds, which is the net current crossing the boundary surface, the charge crossing per unit time, and on the right hand side we have time rate of decrease of charge within that volume, and the decrease is indicated by this negative sign. Now to that equation 3, we can apply the Gauss divergence theorem on the left hand side because we have a surface integral, and that can be converted into the volume integral. And according to Gauss divergence theorem, we have the surface integral of some vector is equal to the volume integral of the divergence of that same vector, and that I've stated in equation 4. So we can plug in the value of J dot ds from equation 4 back into equation 3. So the left hand side, instead of J dot ds, surface integral now becomes divergence of J dv volume integral. And of course the right hand side at the moment remains the same, that is negative del rho upon del t dv. So that gives us our equation 5. Now the volume that we have chosen is arbitrary. So if the volume is arbitrary, what I can do is I can combine these two equations, bring this equation onto the left hand side. And that I can do by just adding negative del rho upon del t dv on both sides. So this one becomes, the right hand side becomes 0, and the left hand side becomes divergence of J dv plus del rho upon del t dv. So let me just show you what I did here. That step is not shown here, but what we've essentially done is we have taken this volume integral of divergence of J You can also write it as del dot J. Okay, and I've brought this to this term to this side and becomes positive. So I have plus del rho upon del T. So taking the volume integral of that dV equals 0. And since this volume is arbitrary, this integrand, which is mentioned here, this integrand must vanish, this integrand must vanish, and that gives us our equation 6, which is the equation of continuity, which is divergence of J plus del rho upon del T equals 0. So that's the idea here. The equation of continuity, it's basically another form of law of conservation of charge. And if you're talking about stationary currents where there is no movement of charge out of the volume, so essentially there's no time decrease of charge within that volume, because if the charge is not going out, then there's no extra charge which can be created from somewhere else. So whatever the volume charge density is at any point of time, it remains same, it's constant. So the rate of change of volume charge density should be equal to 0, that is del rho upon del T. The term doesn't exist, so we have divergence of J equal to 0 for places where the charge is not changing or there's no volume charge density anywhere, there's no free charge present anywhere. So that's a special case of equation of continuity. So this is how we derive the equation of continuity. Next, we're going to look at Maxwell's equation. So Maxwell used 4 basic laws of electricity and magnetism, converted them into 4 differential equations, coupled them to get 2 differential equations, one in terms of electric field E and the other one in terms of magnetic field H. Of course, they were similar in form. Solved them and then used that to get various parameters of electromagnetic waves, including the speed of light. And that we're going to do in subsequent chapters. So at the moment, we're going to try and pick up those 4 basic fundamental laws of electricity and magnetism and convert them into differential equations, and hence this topic, Maxwell's equations in differential form. So the very first law that Maxwell chose to convert, which gave him his first equation, was Gauss Law in electrostatics. And the statement of the law is that the net flux passing through a closed surface is equal to 1 over epsilon 0 times the total charge contained within the volume enclosed by that surface. So we've seen that in our earlier lectures, this particular law, which is Gauss law in electrostatics, and we also know that epsilon 0 is the permittivity of free space. So equation 1 here is basically Gauss law in electrostatics, the mathematical form. And we also know that the charge, if we have certain volume charge density, if we are aware of the volume charge density of that region, then charge can be represented as volume integral of rho dV, which is our equation 2. And we can substitute the value of Q from equation 2 in equation 1. So we arrive at equation 3, which says that surface integral of E dot ds equals 1 over epsilon 0 times rho dV. Now if we take epsilon 0 onto the left hand side, then it becomes epsilon E, which is the electric displacement vector. So I'm going to make that small change and obtain my equation 4. So replacing epsilon 0, you can multiply epsilon 0 on both sides of the equation. On the right hand side, it's factored out. On the left hand side, your E is converted to D, which is the electric displacement vector. Now, on the left hand side, we have a surface integral. On the right hand side, we have a volume integral. So we can apply Gauss divergence theorem to convert the left-hand side term into a volume integral, and hence make both the equations kind of homogeneous. Both sides we have volume integral. And using Gauss divergence theorem, as we had discussed earlier, the surface integral of any vector is equal to the volume integral of the divergence of the same vector. So we get divergence d dot dv volume integral equals rho dv volume integral. Now, since on both sides now we have the volume integral, we can bring rho dv onto the left hand side. There you go. And club it under the same integral. So we have volume integral of divergence d negative rho or minus rho dv equals 0. Now, since the volume is arbitrary, the integrand on the left hand side should vanish. That is, divergence d minus rho equals 0 or divergence d equals rho. So this is Maxwell's first equation. The equation 7 represents Maxwell's first equation, which says that the divergence of the electric displacement vector is equal to the volume charge density. And if there's a place which is free of charge, you have a region where the charge density is 0. In that case, of course, the right hand side becomes 0, and you get equation 8, which is another form of Maxwell's equation, which is for a charge-free region like the vacuum. If you're talking about electromagnetic wave propagation in the vacuum, there, of course, you'll have to use this condition for the first equation, that divergence of d equals 0. So with that, we conclude this particular session. Now we are left with 3 differential equations and 3 other laws from electricity and magnetism. So in the next lecture, we're going to convert those 3 equations and get the full set of Maxwell's equations in differential form and integral form also. We're going to discuss how to get the integral form of Maxwell's equations from the differential form. Thank you, and I'll see you in the next.